Hello class. I've changed the position of the camera so you can get a little closer. There's only about a meter of space between the fridge and the camera. You should be able to read it even on your phones now. Anyhow, I'm going to review the test that I gave you on April 28th. Comprised of questions 16, 18, 30, 56, 88, and then the sulfuric acid question. The first question asks you to identify acids, bases, and their conjugates. So in 18, it shows you hypobromous acid and water. So this is the acid. So A stands for acid, B for base, Ca stands for conjugate acid, Cb for conjugate base. So this is the acid, there's its conjugate base. Here's the water acting as a base, and then once it's been protonated, it becomes the conjugate acid. You'll notice water is amphiprotic, meaning if you put it with a strong acid, it behaves like a base. If you put it with a strong base, it behaves like an acid. Okay. Then you have the bisulfate anion. This is the anion that results after the first ionization of sulfuric acid. You get the bisulfate anion. That's a weak acid, but it's still an acid in its own right. And it can lose that proton to give sulfate. So that's the acid, that's the conjugate base. Then you have the bicarbonate anion, which is behaving like a base in this case, in the presence of the bisulfate anion. It gets protonated, forms the carbonic acid, which if you were to continue it, the carbonic acid would break down into water and carbon dioxide. It would fizz out. And the next one is the bicarbonate anion, behaving as a base in the presence of a hydronium ion. Then the hydronium ion, once it becomes deprotonated, becomes the conjugate base, turns back to water, and then the conjugate acid is the H2SO3. Sulfurous acid is that would be called sulfurous acid. On 1630, the question is, calculate the hydroxide ion concentration for each of the following solutions and indicate whether the solution is acidic, basic, or neutral. In A, the proton concentration is 0.0075 molar. So that's what you're starting off as your condition. Remember, use the ion product of water to solve for it. The hydroxide ion concentration times the proton concentration in water at 25 degrees Celsius is always 10 to the negative 14, which we call Kw. So Kw divided the H plus concentration is going to give you the concentration of protons, 1.3 recurring, times 10 to the minus, the hydroxide ion concentration is going to be 1.3 recurring times 10 to the minus 12. As soon as it falls below 10 to the minus 7, you know that it's going to be acidic. All right, if the hydroxide ion concentration exceeds 10 to the negative 7, then you have a basic solution. So the break-even point is when they're both 10 to the negative 7. That's how they get the pH scale. Because pH is equal to negative log of the H plus of the H plus concentration, and POH is the negative log of the OH minus concentration. Both of them come out to 7 in water because of autoionization. So a tiny amount of water breaks down, even at room temperature, into hydronium ions and hydroxide ions. Although, and I say hydronium, but sometimes people will portray it as an H plus. H plus per se is not sitting there by itself in solution. It's always solvated. It's always combined with a water molecule. And then the hydronium ion itself is surrounded by water molecules that have oriented their oxygen atoms towards the plus charge of the hydronium ion to sort of shield it and create a sort of a hydration sphere. B, the initial condition is that H plus concentration is equal to 6.5 times 10 to the negative 10. So the hydroxide ion concentration is Kw over the H plus concentration. You get 1.53 times 10 to the negative 5, which means it's a basic solution. In part C, the H plus concentration is, let me just double check that one, 1630 C. A solution in which the H plus concentration is 10 times greater than the OH minus concentration. So H plus concentration is equal to 10 times OH minus concentration. Let X equal to H plus concentration. Therefore, the OH minus concentration is going to be 10X. And X times 10X has to equal Kw, which is 10 to the negative 14. Solve for X, and you get X is equal to the square root of 10 to the negative 15. And therefore, when you take the square root of that number, you get 3.16 times 10 to the negative 8. 10 times that gives you the hydroxide concentration, which is 3.16 times 10 to the negative 7. So there's your two answers. In the last part, you're asked to calculate the Ka value. No, not that. 1656. 0.1 molar solution of bromoacetic acid is 13.2% ionized. Calculate H plus. Okay, you can set it up like an ice table to show all the values. Remember, you start off with 0.1, and then you get 13% ionization, 13.2% ionization. So that gives you this concentration of H plus and this concentration of the bromoacetate anion. Now you subtract that number from 0.1, you get 0.068868. So that gives you the three concentrations at equilibrium. It's 0.0132 molar for the proton, 0.0132 molar also for bromoacetate anion, and for the undissociated bromoacetic acid, it's 0.0868. So, question 1688 asks you to identify an unknown based on some conditions. It says an unknown salt is either potassium bromide, ammonium chloride, potassium cyanide, or potassium carbonate. If a 0.1 molar solution of the salt is neutral, what is the identity of the salt? Well, remember that we're told in the lesson that when you have the counter ion of a strong acid or a strong base, that ion has no pH activity. It does not cause water. It does not pull a proton off water or add a proton to water to create a hydroxide or the hydronium ion. So because potassium comes from potassium hydroxide, or can be seen as with potassium hydroxide, which is a strong base, then potassium has no effect on pH. Bromine is the anion for hydrobromic acid, which is a strong acid, so the bromide ion has no effect on pH. So KBr will have no effect on acidity or basicity. So, I mean, if you got lucky in an exam and you came across that one and you're in a hurry, you could splash down that answer and it's the correct answer. But let's analyze all the other ones to prove that KBr is in fact the only one that could be the salt that has no effect on the pH. If it was, so the answer I wrote is both ions are counter ions of strong acids or a strong base. KOH is a strong base and HBr is a strong acid. The conjugate acid and conjugate base of a strong acid and strong base do not exhibit basicity or acidity respectively. That's quite a mouthful, but take a moment to think it over carefully and you'll see it makes sense. Ammonium is a weak acid. So if you had ammonium in solution, you would get a pH less than 7. So it can't be ammonium chloride. The other possibility is potassium cyanide, but cyanide is a weak base because the cyanide anion can pull a proton off water to generate hydroxide. And likewise, the carbonate anion is a weak base. They call it washing soda. If you have a potassium carbonate, for example, that's the substance they use in your washing machine because it doesn't sud, but it raises the pH enough so that it helps clean the plates and so on, just from the sheeting action of the water on the plates and cutlery. You can't have anything sudsing. You can't have detergents in a washing machine, or else it makes a bubbly mess. So the carbonate anion will make the pH higher than 7, so it's a weak base. So the salt must be potassium bromide because it's the only one that will give you a pH close to 7. Okay, the next two questions, no, sorry, the very last question is the sulfuric acid question, so I'm going to have to erase to make room for it. Just bear with me as I take care of that. This erasing procedure is harder than it looks. It's basically a 3-step procedure. Got to use the Windex to take off the most of it. Then you have to follow up with alcohol to get off the last bit of residue. But for the alcohol to work, you have to wipe it off with a damp cloth. And then once that's done, you have to follow up with a dry cloth because the surface has to be dry before I write on it, otherwise the marker stops working. It's a 3-step cleaning procedure. I ordered my dry erase board today. I finally got my confirmation number, so I'm going to go pick it up tomorrow and possibly head down to the country. They want to arrest me on the way for traveling, for committing the sin of traveling. There we go. Now we get that last bit of residue off with the isopropyl alcohol. Look at that. It works pretty well. Except I broke my pump by dropping it just when I needed it. This is going to be the most educated fridge ever. Okay, now the last question I gave you was, what is the pH of a solution of sulfuric acid with a concentration of 0.0033 molar? So we know that sulfuric acid, that's still moist. I gotta. Okay. We have sulfuric acid is a strong acid for the first dissociation. It yields the bisulfate anion and a proton. That's actually, we wouldn't even draw an equilibrium arrow for that because it goes, oh, why did I do that? Why, oh, why? Okay. A costly mistake. Whoops, daisy. Okay. Put an arrow for that one. Okay, and then I just smeared my fork. The bisulfate then is a weak acid, and it results in the dissociation again to form the sulfate anion and another proton. So the first dissociation, right away you're going to get 0.0033 moles per liter of H+. But now for the second dissociation, where Ka sub 2 is equal to 1.2 times 10 to the negative 2, you have to do a calculation. You can't, like a lot of you did on the test, just say, well, you can approximate the pH by looking at the first dissociation. That works most of the time. It doesn't work for this situation. You have to do the calculation, especially when it's dilute sulfuric. If it was concentrated sulfuric acid, say if the pH was below 3, you could get away with that estimation and it'd be fine. But because it's a dilute solution of sulfuric acid, you have to include the second dissociation to get a correct answer. So what do? You set up an ice table. Not a nice table, but an ice table. You can also set up a nice table if you want, if you're nice. So it starts off at 0.0033, and a certain amount of it dissociates, and at equilibrium will be 0.0033 minus x. This starts off at 0, and x amount of it dissociates, and equilibrium you have x. This starts off at 0.0033, and then an additional amount comes into solution. So at equilibrium it's going to be 0.0033 plus x. So notice this one is at minus x, that one's plus x, kind of cool. You're going to get a trinomial when you solve. When you set up the equation, remember that Ka sub 2, can you see? No, you can't. Let's fix it. Ka sub 2 equals 1.2 times 10 to the negative 2, which equals or represents the concentration of the sulfate anion times the concentration of additional protons dissociated plus the over the original concentration of bisulfate, and that's going to be represented here by x times 0.0033 plus x all over 0.0033 minus x. So that creates a trinomial. I'm just going to go jump straight to the trinomial, but you'd say 1.2 times 10 to the minus 2 multiplied by the denominator over 1, and it creates a line, and then with that you can just transpose everything. Once you finish doing that, so skipping all the algebra, well, not skipping it, here I'll show you what it looks like. You can stop the video and copy if the skip is too hard for you. There it is. So what you get is a trinomial, x squared plus 1.53 times 10 to the negative 2 x, I didn't put the x, I just noticed I had a little mistake in there, minus 3.96 times 10 to the negative 5 equals 0. Let me put that x in there because I just showed you something with a little mistake in it. There. Here it is. I had a mistake, tiny mistake, which I didn't even notice, but there was supposed to be an x next to that one. I just put in the x now, next to this one. Okay? So now you have the correct version. That gives you a trinomial. You plug that into the quadratic formula, you're going to get two answers. The first answer is going to be 2.2556 8019 times 10 to the negative 3. And the other answer is going to be negative 1.7556 times 10 to the negative 2. So this is the correct answer. That's not possible because it's negative. So it's 8. This is the H plus concentration from the second dissociation. But remember, you still have the H plus from the first dissociation. So the total H plus, let's call it H sub T, the total concentration of protons in the solution is 0.0033 plus this number, 2.255, etc., times 10 to the minus 3. What you get at the end is H plus concentration equals 5.55568019 times 10 to the negative 3. And if you take the log of that, so pH equals negative log of 5.55, etc., times 10 to the minus 3, and it's going to give you 2.2552, and you're going to report it as 2.26. That's the pH you get. for a 0.0033 molar sulfuric acid solution. I got one last thing I want to do with you, and that is review the answer to page 743 practice example. So that's on 743. Let's go there. Yeah, it's right. It's finding the concentration of lanthanum. I have that here. Thank goodness for doing work ahead of time. Now I gotta erase again. That should be enough. Let's do the second phase. Cleaning. Question asks on 743 the KSP for lanthanum fluoride is 2 times 10 to the negative 19. What is the solubility of lanthanum fluoride in water in moles per liter? Let's start by showing what the equation looks like. This is practice example page 743 on the text. So it shows lanthanum fluoride looks like this, and dissociates into the lanthanum cation and 3 fluorides. Now it's not going to be very soluble, it's got a low solubility. Its KSP, we are told, is 2 times 10 to the negative 19, and what it represents is the concentration of lanthanum cations multiplied by the fluoride ion concentration raised to the power of 3. So we'll let X equal to the lanthanum ion. I'm going to put fluoride. So we're letting it equal to lanthanum ion cation concentration. If that's the case, then 2 times 10 to the negative 19 is equal to X, lanthanum, times 3X, because fluoride, remember fluorine, there's going to be 3 equivalents for every equivalent of lanthanum fluoride that dissociates. So you're going to have 3 times as many fluoride anions as you do lanthanum cations, and also don't forget to raise it to the power of 3. When you simplify that, you're going to get X times 27X cubed, because 3 times 3 times 3 gives you 27. And of course, X is cubed because X times X times X, and that simplifies yet again to 27X to the power of 4. So that means that 22 times 10 to the negative 19 divided by 27 is going to give you X to the power of 4, and that equals 7.407 recurring times 10 to the power of, oh, I got a misshapen 21 here. Let me double check before I have you freaking out saying that the answer is wrong. 2 exponent negative 19 divided 27. Yeah, 7.407 recurring times 10 to the power of 21. Now what you do is you take the 1/4 power of both sides, right? So if you take x to the power of 4 and you raise it to the 1/4 power, you're getting x to the power of 1. Do the same thing on the other side. You can do that. So to the negative 21 raised to the 1/4 power, you're going to get the value of x. So x equals, are you seeing this? No, you're not. You're going to get, better just sit down. 9.2771922 times 10 to the power of negative 6. So that means the lanthanum cation concentration is equal to 9.28. You're only allowed 3 sig figs, I think, times 10 to the negative. Yeah, oh, you're only allowed 1 sig fig. Yeah. Okay, you're only allowed 1 sig fig, but I don't know why the book pulled. But that's the answer you're going to get. So because their value of Ka only has 1 sig fig in it, theoretically we can only go to 1 sig fig. So we're going to write 9 times 10 to the negative 6. The book says 9.28. You can see why. But the book isn't following its rules. Bad book. That's the concentration of lanthanum that dissociates into the solution. Let's see if we can do one more thing. There's one calculation here where you do an approximation. How much time have we used up here? We can maybe do another 3 minutes. Upcoming notes talk about selective precipitations, and then there's this homework. You know what? Here's what we're going to do. Try this tonight. Factors that affect solubility. Try the practice exercise on page 745. See if you've mastered this whole notion of making approximations. And I'll give you a hint for 740. For the practice example on page 745, you might have to ignore the x part at some point, because it's going to be such a small number that it's hardly going to put a dent on the other number. So with that hint, see if you can solve for the answer on practice example on page 745, and I'll see you tomorrow. All right, see you tomorrow.